Assalamualaikum viewers, please like, share and subscribe this channel. Links of PDF files used in this video are given in description. So today is a part 4 of a lecture series about metal carbonyls, and in this particular lecture we have discussed structures of metal carbonyls, especially binuclear and polynuclear molecules. So bonding situation in metal carbonyls with special reference to multinuclear types. So first example is this, and this is deca-Carbonyl di-Manganese. So the structure of this is like this, that there are two manganese atoms. They are not only linked with each other through metal-metal sigma bond, but each manganese is attached with 5 other carbonyls. So let's see how these are arranged. So overall charge on the complex is 0, carbonyls is 0, so manganese also have a 0 charge. So the electronic configuration of manganese is like that. Its atomic number is 25, so 4s2 3d5 is its valence shell electronic configuration. Now this configuration has been written in this form, so it is actually 4s2 3d5. So this is the valence bond theory or VBT type of writing the electronic configuration. Now as carbonyls are strong field ligands, so we will use again a steric and we will do a rearrangement, but here we will do a peculiar rearrangement, and as compared to the previous examples we will not pair up all these electrons, but we will pair up them by according to our needs. So first of all, if we are seeing here that in order to draw this bonding situation, now actually there are two manganese atoms, so one is represented by manganese type A and second is represented by manganese type B. If we are seeing here in this picture that each is attached with 5 carbonyls, or we can say that each manganese atom is attached with odd number of carbonyl molecules. So whenever there are odd number of molecules, then what we will do, we will draw two molecules of carbonyl in which there is no back bonding, and in remaining we have to show the back bonding. So this is basically a rule and we have to follow it in order to draw the bonding situations. So first in manganese A we have shown two carbonyls with A form in which there is no back bonding, and here green cross are the electrons only contributed by the manganese. Similarly in the manganese B atom we have drawn two carbonyls with A form in which there is no back bonding, and then there are three carbonyls which are equally contributing two electrons from their sp hybrid orbital and form three in total 5 coordinate covalent bonds, and all are sigma. But in these three there will be back bonding and these will be in B form. So here are the electrons of metal which have been used for back bonding, and here 3 pi coordinate covalent bonds are formed both in A, and similarly in second B atom the same situation is that there are two forms in which there is no back bonding. There are three carbonyls as such that in which there is back bonding, and these are actually in B form, and these are the electrons all contributed by the carbonyls, whereas these three arrows are indicating back bonding electrons, and these electrons are donated towards carbonyl from the metal through pi bond. Now in order to confirm that either our electrons all have been included or not, so if we see here the number of manganese atoms are 1 2 3 4 5 6 7, so there are total 7 number of electrons. So 1 2 3 4 5 6 and 7 electrons are there. Similarly 7 electrons are in manganese B. Now one new thing is this bond, which is called as metal metal sigma bond, and in the diagram this bond has been represented here. So this electron or orbital of metal overlap with this electron containing orbital of metal to form a metal metal sigma bond. So this is the overall bonding situation of deca-Carbonyl di-Manganese metal carbonyl. Now if we see here that in this diagram we have not drawn the structure according to the geometry. We just randomly attach 5 carbonyls with one manganese atom, 5 with other, and both are attached with sigma bond. But if we see the geometry of this complex and arrange them according to some particular bond angle, so actually there are two octahedral structures. So one is this, in which 1 2 3 4 and 5 6 ligands are attached like this, and other octahedron is this, like in this, these two carbonyls, these two bonds making 4, and these actually making 6 bonds. So actually the geometry of this Mn2CO10 metacarbonyl is jointed octahedron, or we can say that two octahedral geometries are jointed together through this metal metal sigma bond. So this was the bonding situation of deca-Carbonyl dimanganese. Now next example is Octa-Carbonyl dicobalt, and this is the general structure of this molecule. So again there are two cobalt atoms A and B. These are jointed together through metal metal sigma bond, and each carbonyl is attached with and each cobalt is attached with 4 carbonyls. So again this complex has zero oxidation state, carbonyl is 0, so metal will be 0. This is the atomic number of carbon, this is the atomic number of cobalt, which is 27, and this is its valence shell electronic configuration. And now when we write this valence shell electronic configuration in the form of VBT, so it is 3d7 4s2 and 4p. Now just like Mn2CO10 which we have discussed earlier, again there will be two cobalt atoms, one we have named A atom and other with B atom. Now one thing important is here again, that as each cobalt is attached with even number of carbonyls, so in half we will do back bonding and in half we will never do back bonding. So here we are seeing that these two carbonyls are those in which there is no back bonding and both are A forms, whereas in next two carbonyls there is back bonding and these are actually the B forms, and these are the electrons contributed by the sp orbital of carbonyl with the orbitals of cobalt. Now as these two show back bonding, so these are the pi electrons which are contributed by cobalt towards carbonyl to form two pi bonds. Now again in order to confirm that all electrons have been included here, if we count the number of electrons in cobalt, so these are 1 2 3 4 5 6 7 8 9 electrons. So we have to justify 9 electrons in this bonding situation. So 1 2 3 4 5 6 7 8 and 9 electrons are there. So whatever we have done in the cobalt 8 atom, similarly we will do this in cobalt B atom. And again there are two carbonyls with A form and two carbonyls with B form, and these are the sigma contributed coordinate covalent bond as shown by the green electrons, and the pi bonding electrons are represented here. So this is the overall bonding situation of cobalt. Now again the each cobalt atom is attached further with other cobalt atom through metal metal sigma bond. So this metal metal sigma bond has been represented here. Again if we see that this is the structure, just to have idea about how many carbonyls are attached, but if we draw the geometry, so if we see here that each cobalt is attached with 4 carbonyls and there is one bond which is metal metal sigma bond. So in overall each cobalt is attached with 5 bonds. So if we see here that there are actually two trigonal bipyramidal geometries. One is this, in which these are equatorial and these are axial positions, and second is this, in which these are equatorial positions represented by these carbonyls and these are the axial positions. So we can say safely here that the geometry of octa-carbonyl dicobalt is jointed trigonal bipyramidal geometry. So this was the bonding situation of Octa-Carbonyl dicobalt. So here is the other arrangement of Octa-Carbonyl dicobalt. Again here there are two atoms attached with sigma bond, metal metal sigma bond, and each with 3 carbonyls. Now the difference is that now we have included 2 bridging carbonyls, whereas in the previous structure there were no bridging carbonyls. So how we can determine that either this molecule of cobalt will have bridging carbonyls or not? So we will take help from the IR. So in this example the IR value is coming around 1850 per centimeter. That is an indication of that there are bridging carbonyls present. So actually octa-carbonyl dicobalt exists in these two forms. In one form there are bridging carbonyls, in other there are no bridging carbonyls. So now this molecule has 3 types of nature of bonds. One is metal metal sigma bond, other is terminal carbonyl bonds, and the last one is bridging carbonyls. Now how these are attached, again we can see here that overall charge on the complex is 0, carbonyl is 0, cobalt has a 0 charge. Now this is the atomic number of carbon and its valence shell electronic configuration is 4s2 3d7. Again this is the configuration written in the form of valence bond theory. So now there are 2 cobalt atoms. If we see in the structure that with each carbonyl there are actually 3, with each cobalt there are actually 3 or odd number of carbonyls attached. So what we will do, we will do 2 carbonyls with no back bonding and remaining carbonyl with back bonding. So if we see here there are 2 carbonyls with there is no back bonding and 1 carbonyl with back bonding or B form. So this is the back bonding electron of cobalt. Similar is the case with the B atom of cobalt. So 2 molecules of carbonyl are attached via A form and one is attached with B form, in which there is back bonding, and here the back bonding electrons. Now in order to indicate 2 bridging carbonyls, what we are doing here, we are them attaching like this. So this is the 1 electron of cobalt and it is shared with the green electron contributed by this bridging carbonyl. Similarly, this carbonyl is making bridge with other cobalt B atom. So this is the single electron of cobalt and this cross is the electron of carbonyl. Same bridging carbonyl is here. So there are actually 2 bridging carbonyls. Third, we are now attached this metal metal sigma bond, and where here we have attached this metal metal sigma bond and remaining electrons will remain as it is in inert form. So in order to confirm that either we have included all the electrons of the cobalt, so total number of valence shell electrons of cobalt are 1 2 3 4 5 6 7 8 9. So there are 9 electrons, like 1 2 3 4 5 6 7 8 9. So we have included all the electrons of the cobalt. So this is the bonding situation of this geometry in which there are bridging carbonyls, and we have indicated these bridging carbonyls by the presence of IR value around 1850 per centimeter. This particular geometry of octa-carbonyl dicobalt is also called as open book like arrangement. So this was all about geometries of octacarbonyl dicobalt.